if we are to make a linear equation into a scientific thing instead of an abstract mathematical thing, yeah, I know, mathematicians, hang with me. What do each of these quantities mean? So starting with x, what role does x play in this equation? Usually. Say again?
Slope.
X?
Oh, sorry.
We can put the slope. Which of these letters represents a slope? The M. And by the way, slope is the big one. Slope is the big thing that gives people indigestion when they take Algebra 1 and Algebra 2 with linear equations. And correspondingly, it is the one that we will spend the most time talking about this week. So M is the interesting one. That's the slope. Okay. We can recognize it as the coefficient of x when y is the subject. The coefficient of x when y is the subject. Okay. All right. So what role does x play? Yeah. Rise divided by y. So a lot of these, this is like a free association game now, right? A lot of things pop up. Slopes, rise over runs, et cetera, et cetera. But in the beginning, this equation is a story. It's a story of a relationship between two quantities, an independent quantity and a dependent quantity. The independent quantity is the one we typically call x. And the dependent quantity, the one we typically call y. Now, when these, helps if I spell quantity correctly. When these quantities are things that have physical reality to them, when they actually stand for something, then x and y will have meaning associated with them. They'll have units associated with them, right? Because they're real quantities that we either measured or we sort of did something theoretically to figure out what they were. So they both have meanings associated with them, and they both have units associated with them. And when x and y have meaning in units, then so do m and b have meaning and units. M being the slope, and b, what role does b play in this whole charade? It's the y-intercept. Or I'm going to call it the vertical intercept. And each one of these things has units and a meaning. As long as x and y have units and meanings, so do m and b. And one of the big performance tasks of this week is going to be to extract meaning. From slopes and from intercepts. That's going to be one of the big things that we do when we have a context for these things. So here's the roles that all of these different things are playing. So let's just take an example. I don't know. So here is a graph that's telling a story. And because the shape of this graph is a straight line, the hint is that probably this is a story about a linear equation, which indicates that y equals mx plus b business will have something to do with this. But the first point I want to make about this is that I don't actually want to use y and x as my independent and dependent variables in this example. Because my example has context, because I'm talking about not xylophones, but time, and I'm talking about not yaks or something, but I'm talking about velocity. So why use x and y when we can use variables to denote them that have better meaning to our problem? So in place of my independent variable x, because we're plotting time on the horizontal axis, let's use t instead. And instead of y on the vertical axis, we've plotted a velocity, so let's make that v. So one of the first steps in figuring out the story that's being told by an equation is making sure that we have meaning for each of the variables. Okay? So if I'm describing this relationship, I'm going to describe it as a relationship not between x and y, which mean nothing, but between t and v, which mean something. They mean time and velocity in this example. And let's suppose that we happen to know what the equation is. Let's say we happen to know that it's v equals, 10t plus 25, or something like that. Let's suppose that's the equation of this line. Well, tell me, what is the value of m for this equation? It's 10, again, because it's the coefficient of the independent variable when the dependent variable is the subject. Right? So it's the coefficient of t when v is the subject. And in this equation, that coefficient is 10. But of course, 10 is not good enough in this class. Because t and v have units, m must also have units. So what are the units of that 10? Meters? Well, if m is measured in meters, t is measured in seconds, what are the units of m times t going to be? They would be meters times seconds, right? Because we're multiplying m and t. So we get this weird meter seconds as the units of m times t. That doesn't seem right. Because what are the units of v on the left-hand side? Meters per second. Meters divided by seconds. So having units of meters doesn't seem to work for m. We know what numerical value m has, but let's do the dimensional analysis to figure out what units the slope in this equation must have. So let's try rearranging this equation to make m the subject. What do you want to do? If I want to make m the subject of this equation, what's my first step? Subtract, right. Addition and subtraction happens first, so we'll subtract b from both sides. And then, to make m the subject, divide by t. Great. So v minus b all over t. It's going to be m. So rearranging this equation to make m the subject, now to figure out what the units of m are, all I have to do is put in what are the units for v, b, and t on the left-hand side. Well, what were the units for v, the velocity? Meters per second. Now, if I'm subtracting b from v, what units did b have to have? If I'm going to subtract these two quantities, what has to be true about their units? Units have got to be the same. So b will also have units of meters per second. B has units of meters per second. After all, b is a vertical intercept, and therefore will have the same units as the vertical variable, the dependent variable. So that's always true. The units of the intercept are always the same as the units of the dependent variable, which is plotted on the vertical axis by convention. But then in the denominator, what are the units of t? Units of t downstairs are seconds. And so my slope, m, is going to have what units? If we simplify, meters per second minus meters per second is going to be, unit-wise, meters per second again, right? Because they're the same units, so when we subtract them, the units remain the same. But then downstairs, I have seconds. Now simplifying, meters per second divided by seconds, what do I get? Meters per second, meters per second squared. Again, why? Because dividing by seconds is the same as multiplying by reciprocal seconds. By the way, a reciprocal second is called a hertz in science. Not that we need to know that, but there it is. And then multiplying those fractions by multiplying the numerators and multiplying the denominators show us what the units of our slope must be. Meters per second squared. And where those units came from, the reason that those units are different from the units of our other quantities in the problem is precisely because of this division sign right there. That, what looks like a fraction, but it's really division. Process of division, as every fraction is. That is what turns the units of the independent and the dependent variables into units for the slope. So, where this all came from is that we took the vertical units, which were meters per second, and the horizontal units, which were seconds, and we divided them one by another. Why? Because what is a slope? I think Mike said this a minute ago, among other things. A slope is a rise divided by a run. In other words, it is a vertical difference on a graph divided by a horizontal difference on a graph. And since our vertical differences are measured in the units of the dependent variable, meters per second, And our horizontal units are measured in the units of the horizontal variable, seconds. The units of the slope will have units of dependent variable divided by independent variable. Meters per second divided by seconds, because it's a rise, a vertical quantity divided by a run, horizontal quantity. So when we think about telling a story with a slope, when we tell a story with a slope, the first thing to do with it is figure out what the units of that slope are going to be. Usually it guides you into the interpretation for what the slope is. In particular, what kinds of quantities in science, particularly physics, have units of meters per second squared? It looks an awful lot like an acceleration.
You said ratio. I said acceleration.
I heard acceleration. I'll take it.
For me, yes.
So figure out what the units are first. And the units of a slope, again, are always the units of the dependent variable, or the vertical, divided by the units of the independent. Because it's a rise over a run, and a rise is a difference in the dependent variable, and a run is a difference in the independent variable. So figuring out what the slopes are will help us to interpret. And so to finish this interpretation, the slope of this particular relationship is 10 meters per second squared. And what was the intercept? The vertical intercept? What's the vertical intercept of this equation?
25.
25, and what units did that have?
Meters
Meters per second.
per second.
So as we work on linear problems for the rest of the day today, have this in the back of your head, because this is going to be the thread that you can pull on to help to interpret a linear equation that comes from a scientific context, to interpret it in that same context.